Section 3.3-3.4 deals with polynomials. So this is an example of a polynomial in standard form. So, well, standard form almost. So standard form normally means that our polynomial is written in order of descending exponents, basically going biggest to smallest. So here, if we were to rewrite this in standard form, this would be the term in front. And so that makes this my leading term. And it would be the term in front because it's got the highest degree. And so the degree of the leading term is the degree of the polynomial. So this polynomial has degree 9. And the coefficient of the leading term is the leading coefficient. So it's got a leading coefficient of -3. Now, when we're talking about end behavior of polynomials, we have 4 different scenarios. We have odd degree and a positive leading coefficient, and that means that your end behavior would look like that. Then you have odd degree and a negative leading coefficient, and in that case, your end behavior would flip over. Then we also have even degree with a positive leading coefficient, and that looks like this. And then we have even degree with a negative leading coefficient, and that would look like this. Okay, I know Andy goes over them in his video, but that's a quick review. So here we're dealing with odd degree and a negative leading coefficient, which means this is what my end behavior would look like. So that means that as R goes to the right, f of R goes down. And as R goes to the left, f of R goes up. Okay. And then the maximum number of zeros is always the same as the degree. So this would also be 9. And the maximum number of turning points is always the degree -1. So this would be 8. So using that information, the fact that the maximum number of zeros is the same as the degree, and the maximum number of turning points is 1 less than the degree, if we look at this polynomial, it has 4 zeros. See, 1, 2, 3, 4, and 3 turning points. 1, 2, 3. So that means its minimum degree is 4. It could be bigger than that. It could be 6, it could be 8, but it can't be 2 because if it has 4 zeros, that means its degree has to be at least 4. And then for our next 2 questions, we're going to write a polynomial given information. So here we're given 2 zeros, one at 5 and one at -3. This is 2 different ways basically to call these numbers zeros. So if we have a 0 at 5, then that means that we have a factor at u -5. And multiplicity is the degree of a factor. So that means that in my function, this u -5 would be to the 2nd power. And so then we also have u equals 3, -3, excuse me. So that means we have a factor at u +3. If they don't tell you multiplicity, then you assume that it's 1. And when something is to the 1st power, we don't write the 1. So we've got a pretty good start for our function. The thing that we're missing right here is the leading coefficient. And I know we sort of touched on this last time when we talked about quadratics, k of u. And that is that in order to find this leading coefficient, we take a point, any point that's not a 0, or if you're dealing with quadratics, not the vertex, and plug it in. And so that's why they gave me this other point over here. They gave me this other point so that I can use it to find the vertex, to find the leading coefficient, excuse me. And so here, that means that when u is 0, k is negative 48. So I'm going to plug those in. Negative 48 equals a times 0 minus 5 squared times 0 plus 3. And then negative 5 squared is 25. And then that's just 3. So then that's going to be 75a. So then when I divide both sides by 75, I can reduce 48 and 75 both by 3. So it'll be 16 over 25. So now that I know my leading coefficient, my function is times u minus 5 squared times u plus 3. Okay. So we're going to do something extremely similar for the next problem, only we're going to figure out what the multiplicity is based on the graph. So here we see that we have a 0 at -2. So r equals -2. And at -2, the graph is crossing straight. See it? Straight through. And then anytime you cross straight, then that means that that 0 has a multiplicity of 1. So I have another 0 here at 1. At 1, your 0 is bouncing. See how it's turning over? Bouncing. And then a bounce means that you have an even multiplicity. But since it says smallest possible, the smallest possible even would be 2. And then last but not least, here we have a 0 at 4. And at 4, this is what it looks like when this 0 crosses curved. And if your 0 crosses curved, then that means it has odd multiplicity greater than 1. Now, since we want the smallest possible, the smallest odd greater than 1 is 3. So then what I have so far is g of r equals, we still don't know that leading coefficient, r plus 2 to the first, r minus 1 to the second, and r minus 4 to the third. And so to figure out what that leading coefficient is, I'm going to take this y-intercept and I'm going to plug it in. So when r is 0, g is 2. So 2 equals a times 0 plus 2, because when the exponent is 1, we don't usually write it. 0 minus 1 squared and 0 minus 4 to the third. Okay, so then a times 2 times a negative 1 squared is a positive 1, and a negative 4 to the third is a negative 64. So I have a negative 128a. And then if I divide both sides by 128, I'll have 2 over 128, which would reduce to 1 over 64. I cut off here whether it wanted decimals, so if it wants decimals, just do the division in your calculator. So then my final answer here would be negative 1 over 64, r plus 2, r minus 1, r minus 4 to the third. So here we have another polynomial in factored form. So in factored form, to find the degree, you add the multiplicities. So here that would be, remember we said when there's nothing there, it's a 1. So 1 plus 4 plus 3. So my degree here is 8. And to figure out the leading coefficient, you basically ignore the constants and multiply the leading coefficients in each term, including the exponent that goes along with it. So like to find my leading coefficient here, I would do negative 0.031 times 4 times negative 2 to the 4th times 2 to the 3rd. Because the idea here is if we were to multiply all of this out, what number would you have in front if you were in standard form? And so to figure that out, you just multiply each one of those leading coefficients. So negative 0.031, 4, negative 2 to the 4th, 2 to the 3rd. And the coefficient is negative 15.872. So then this polynomial has even degree and a negative leading coefficient, which means its end behavior is down and down. So then that means as t goes to the right, h of t goes down. And as t goes to the left, h of t also goes down. So to find the t-intercepts, we would say, where does this equal 0, right? We change this to 0 for t-intercepts. But if I'm multiplying all of these together and their product is 0, it means one of them has to be 0. So to figure out the t-intercepts when you're in factored form, you just set each factor equal to 0 and solve. So I'm going to add this 7 and divide by the 4. There's my first 0. I'm going to add the 9 and divide by the negative 2. I'm going to add the 9 and divide by the 2. Now, if you don't want to do it that way, a note that you could always put this in the calculator. You could always graph it and then do calc 0 and find the zeros that way. Okay, now for the h of t intercept, remember h of t intercept is going to be where t equals 0, so that would be negative 0.031 times negative 7 plus 4 times 0 times negative 9 minus 2 times 0 to the 3rd, 2 times 0 minus 9 to the 3rd. And so 0 cancel, cancel, cancel. So I wind up with negative 0.031 times negative 7 times negative 9 to the 3rd times, ooh, that should be a 4. Whoops. 4, 4, times negative 9 to the third. So 0, 3, 1, negative 7, negative 9 to the fourth, negative 9 to the third. We want it to be 0, comma. I forgot the negative sign. There we go. Okay. All right, so this one's going to look a lot like the other one. So a degree we would add them 76 plus 1 plus 97. So the degree here is 174. The leading coefficient would be this negative 11.7, but this is a 1. This is a 1. This is a 1. So it would just be the negative 11.7. So we have even negative again. So this is going to be the same as the last one, where when t goes to the right, h of t goes down. And when t goes to the left, h of t also goes down. Okay, so this is why I actually wanted to do this one. So when we're graphing h at negative 8, because you have even multiplicity, so that's this part over here, the graph would bounce. At negative 6, your multiplicity is 1, so your graph would cross straight. And at 9, your multiplicity is an odd number that is greater than 1, which means that your graph would cross curved. Those are the rules we just talked about on the graph on the other side, right? Same rules, but sort of going the other way. Before we used the behavior to determine the multiplicity, and now we're using the multiplicity to determine the behavior. Okay, last but not least, here we have this term has the highest degree, so that makes it the leading term. So a degree of 3 with a leading coefficient of 9. So odd degree and a positive leading coefficient means my end behavior looks like that. So this means that as r goes to the right, h of r goes up. And as r goes to the left, h of r goes down. Now, just like I mentioned before, if you don't want to solve this algebraically, you can always graph this and then do calc 0. But this one factors. So 9r to the third minus 6r squared minus 81r plus 54. First of all, there is a GCF of 3 here. So if I take out a 3, I would have 3r squared minus 3r to the third, minus 2r squared minus 27r plus 18. And now I'm going to ignore that GCF for a second and factor the inside by grouping. So a 3r squared and a 2r have an r in common. A negative 27 and an 18, I could take out a negative 9. Well, those have a, so then don't forget this GCF. Those have a 3r, that should be an r squared. Those have a 3r minus 2 in common, and that would leave me with this r squared and this minus 9. And then r squared minus 9 factors. 2r minus 3r plus 3. And so then just like before, in factored form, I would set each factor equal to 0 and solve. So 3r equals 2, r equals 2/3, r equals 3, r equals negative 3. So then my intercepts would be at, that's not negative, it's positive, 0.667, 0, 3, 0, and negative 3, 0. And my h of our intercept, if I were to make this r value 0, well then this would turn to 0, this would turn to 0, and this would turn to 0, and all I'd be left with is that 54. So that is what I had for you guys. I am all done. I hope you guys have a wonderful spring break. If I don't speak with you, please make sure that you do something fun and then tell me all about it.